you are hearing me. Hello, everyone. Uh, I'm glad to have this session, and my name is Hamid Tabani from Barcelona Supercomputing Center. We are having a session almost 2 hours entitled Challenges and Opportunities Towards Full Autonomous Driving. And there's lots of things that I'm very interested to talk about. We like to wait maybe a couple of more minutes to see if there are more attendees joining the session, and then I will start talking about the session. So I will be the only presenter of this session. Uh, you have the Q&A panel so that whenever you have any question, feel free to drop your question and I will be glad to answer it. I try to check the Q&A every every time that is part of the section is finished. And if there is anything that I can comment there, I will do so. Otherwise, I will refer all the and answer all the questions at the end of the session. So maybe I can start sharing my screen. Okay. So let's get started. We are like 4 minutes behind the exact time. Again, hello everyone. Good afternoon. My name is Hamid Tabani from Barcelona Supercomputing Center from Barcelona, Spain, and I'm glad to have this thematic session at HiPEAC. Unfortunately, due to this problem of COVID, we couldn't meet physically in the conference, but it's a good opportunity to have this virtual conference, and I'm glad to have this session today with all you. Uh, the session entitled Challenges and Opportunities Towards Full Autonomous Driving. And I am going to present our activity mainly in our group, Computer Architecture and Operating System Group at Barcelona Supercomputing Center. We are working on many directions about autonomous driving and mainly in terms of safety systems and standards. And I'm going to start with agenda first. So basically, uh, let me just stop the webcam so that I can focus more on the slides and there is no overlap between uh, the, the windows. Basically, I'm going to start to have an introduction on autonomous driving systems, and then I will go over the extensive use of deep learning in autonomous driving systems, which is, I would say, a game change in the market and also in the industry of automotive. We are talking later about accelerating compute-intensive modules and functions in autonomous driving systems. Then I will go a little further on discussions related to safety standards and certifications requirements for these systems. And I will highlight some of the main existing challenges that we are facing towards certification of autonomous driving systems. And also, lastly, I will try to cover some parts related to timing analysis and resource usage of advanced autonomous driving systems, because this is also one of the key topics for autonomous driving systems. So basically, autonomous driving systems, I will start with an introduction. What is autonomous driving system? What is the market analysis that we are seeing? Some of the existing challenges, the industry status, and a taxonomy of the different levels of autonomous driving systems. I will later discuss about design constraints, performance, predictability, thermal and power constraints. I'm going to discuss about a industry level autonomous driving software stack, which is developed by Baidu, China, which is called Apollo. And I'm going to refer to Apollo as a case study, but most of the autonomous driving systems actually have similar software stacks. So most of the discussions that I'm going to say here can be simply extended, and they are valid for most of the systems that are today existing. We are going to make a characterization of the autonomous driving systems, accelerating the autonomous driving uh, software, and also an end-to-end performance and power analysis of the autonomous driving system. So let's start with market view, challenges, and taxonomy. Uh, Well, in the past few years, almost all the high-tech companies and car manufacturers have moved uh, to and started actually working on autonomous driving systems. Companies such as Google, Uber, Tesla, Apple, Nvidia, and many other companies, including the top-tier car manufacturers, are all investing lots of money on autonomous driving research and development. Uh, and the investment actually continues in the past years. For example, Intel acquired Mobileye, which it was a leader in computer vision-based autonomous driving system for more than $15 billion. And there are some estimation or predictions of the market by future. For instance, there has been an estimation, a prediction by 2035, saying 15 years from now, that the autonomous driving market will include 25% of the whole automotive market. So that will be like 18 million vehicles per year. And the size of the autonomous driving vehicle market will be uh, surpassing simply $100 billion. Uh, Basically, despite all the recent advancement in autonomous driving systems, uh, we are still having lots of things related uh, to research and experimentation, because we still believe that most of the companies and the research on this domain is in the beginning of its path, and there are a lot of things to explore, and lots of things are still unclear. That some of them I am going to discuss what are the existing challenges uh, and how the industry and the researchers are going to tackle them. Let's start by having a taxonomy of autonomous systems. We have a society of automotive engineering, which is called SAE in abstract, which they have proposed a taxonomy for autonomous driving and autonomous vehicles, in fact. It is including 6 levels. Some they say it is 5 levels, but I mean they are all the same. We have level 0, which is simply there is no automation at all. We are very familiar with these kind of vehicles that have been around for decades. There is nothing related to automation, and the human driver is responsible for all the driving tasks. We have level 1 according to this taxonomy, which is called driver assistance, and that is uh, the the system basically shares the steering and acceleration, deceleration responsibility only under some limited conditions, and still the driver handles all the remaining tasks. For instance, a cruise control system can be fall into this category, which is doing some form of fixing the speed of the car, but the driver is responsible for example, doing a lane change. A more advanced level, which is level 2, we have partial automation, which the system is able to control and steer and doing the acceleration, deceleration of the vehicle, still under limited driving condition. But again, the driver should be there, the human driver should be there for doing the remaining driving tasks. So just for these 3 levels, you see that the automation is still at driving assistant mainly. It's not responsible for doing full driving, and the human driver is responsible for most of the work and the driving task all the time under all conditions. Next, we have level 3, which is conditional automation. In this level, the vehicle may be able to handle all driving tasks, but again, under limited driving conditions. The human driver should be there and should respond to the request to intervene. If something goes wrong with the system can simply put back the responsibility to the human driver and simply stop doing what it's supposed to do. And it is the driver that has to take care of the vehicle if something goes wrong. A more advanced level is the high automation, where the system can do more things, and still it is not full automation that we don't need a human driver. The human should be there. And in some conditions, the human driver is responsible to handle the tasks, but in most of the cases, the system is capable of handling the vehicle. Lastly, it's the full automation, or level 5, which is the main objective of all autonomous driving vehicles, to have fully autonomous driving, which the system takes full control of all the driving tasks under all driving conditions that can be managed by a human driver. And in fact, a vehicle with this level of autonomy doesn't need to have any driver anymore. And all the vehicles that we see without drivers, and they are safe, the prototypes or advertisement that we are seeing are the objectives that companies want to achieve and reaching this level of autonomy. So in summary, for these 3 last levels, you see that the autonomous system can take full driving responsibility at level 3 to 5 of automation under certain driving conditions. And in the level 5, it should be able to manage all the things that a human driver is capable of. So where we are in the current industry status, basically we have companies that are today achieving level 2 and 3 of automation, and in fact they have products in mass production with a capability of level 2 and level 3. And regarding the computing platforms, they are using different systems, such as system on chips that are specifically designed, or they are generic. They are using GPUs, graphic processing units, in order to provide a large amount of computational capacity, which is required for autonomous driving systems. You know that I will explain this in the following slides, but just to say that the autonomous vehicle has lots of sensors in order to identify uh, the surrounding of the car, like what is going on, where the car is, what are the objects that are close or surrounding the car. Um, and here is a category which is discussed in this reference. You see that from different manufacturers like Mobileye, Tesla, NVIDIA, Audi, and Waymo, we have level 2 and level 3 uh, level of automation. Mobileye uses only system on chips, no GPUs, and they are using mainly camera for visualizing the surrounding of the car. Tesla is using system on chips and also GPUs, but they also use ultrasonic sensors, which are radars. Audi, now, for example, we have the Audi A8 in mass production, which is capable of achieving level 3 automation. It is again using system on chips and GPUs, but they are using lidars, cameras, and radars, and the same for the Waymo. There are other manufacturers and prototypes, but we are not, I mean, discussing all the existing prototypes and vehicles. So let's talk about the autonomous driving pipeline to see, in fact, what is autonomous driving system look like. So for this purpose, I am going to talk about a case study which is called Apollo. Apollo is a end-to-end software stack for implementing autonomous driving system, and it is actually the largest autonomous driving project which is publicly available, with more than 120 OEMs, tier 1 and tier 2 AI companies and car manufacturers. It is from Baidu, China, and it is actually considered as one of the most sophisticated open source projects that is implementing the entire autonomous driving software stack. As I said in the earlier slides, most of the autonomous driving systems have similar software architecture, but for the purpose of having a clear idea how these systems are working, in this session, I am just discussing on Apollo. So here you see the Apollo software architecture, which is composed of several modules which are communicating together, and in fact, they are the data that is processed by one of these modules, uh, and the outcome of one module can be used in another module and will be, in fact, as an input to the next module. We have several modules, as you see here. We have the perception, which identifies the area surrounding the autonomous vehicle by detecting objects, obstacles, and traffic signs. And it is also considered as the most critical and complex module of the autonomous driving system. Uh, Perception module fuses the output of several types of sensors, like uh, point clouds, which are the lidars, the ultrasonic sensors like radars, and also the cameras, in order to improve the accuracy. Then we have prediction, which is responsible for anticipating the future motion trajectories of perceived obstacles. We have planning module, which is planning the spatio-temporal trajectory for the autonomous vehicle to take. We have localization. Again, this is one of the key modules in any autonomous vehicle, which estimates where the autonomous vehicle is actually located precisely, using various information sources and sensors such as GPS, LiDAR, and IMU. We have the control unit or control module, which in fact executes the planned spatiotemporal trajectory, and it is going to generate control commands such as accelerating, braking, and steering uh, for the car to take. We have routing or navigator, which tells the autonomous driving system how to reach to its destination via a series of routes and lanes. We have the HD map. It is like, in fact, uh, ad hoc structured information of the roads, and it is like a library working as query engine support. We have the canvas, which is the interface that passes all the control commands to the vehicle, and it also passes the vehicle information back to the system. We have other modules such as Guardian, which is a safety module, and we have the monitor, which is controlling all this behavior. We have the uh, human monitor interface, which is like an interface for the user. So now I would like to focus on the perception module. As I said, this is one of the key modules in any autonomous driving framework. Uh, it is in charge of detecting the obstacles that are surrounding the car, and it usually uses different forms of sensors, such as cameras, which are generating images, and lidars that are producing point clouds, radars that are generating ultrasonic data, and also fusing them uh, to understand uh, better what are the obstacles surrounding the car in terms of where are they, what is their position, what's their size, their orientation, and other information. Here, for instance, you see a point cloud. Here in the center, we have the car, and here you see that the point cloud is showing basically the surrounding of the car. It is not like a camera which you can simply detect what are the objects, but it is a very helpful way of identifying the surroundings of a vehicle. So, in fact, there are a lot of things related to the perception module, why we have different sensors, what are the features, pros and cons of each of these sensors. I'm not going to discuss in detail any of this, but I would like to say that we have different form of configurations for the perception module. As you see, as I said in the earlier slides, different autonomous vehicles may have different forms of sensors and different configurations. So the global configuration of input sensors and processes basically can be represented as a direct acyclic graph, or a DAG actually, like one of these or these ones. Uh, for instance, here we have a DAG for a system, a perception module, which has a camera and a radar. You see that the camera is processing some input images, and then it provides the data to the lane post-processing uh, unit. We also have the radar, which has all other information, and then all these going to be fused in the fusion module in order to have a more understanding of the objects around the car. In another configuration, we may have, instead of a camera, we may have a LiDAR, uh, which is doing more or less similar to the camera, but with a different purpose. And then again, we have the radar, which is going to be lately fused with the data of LiDAR. And we also have probably another configuration like only a camera, which we are going to detect the traffic light, and we process that in a module or in a function. So Let's go back to this slide here. So I showed that we have the software architecture of an autonomous driving system, which are lots of modules, which are communicating to each other, and they are sending data and also control commands. And this is usually going to be done in different ways, but one of the uh, very uh, common ways of doing this is to use a robot operating system or ROS, which is a set of libraries, software libraries, and tools that help building robot applications. In fact, this is very, very commonly used and very popular in the robotic domain. And since in the beginning of development of autonomous driving systems, we had a lot of common features with the robotic systems, the developers have decided to use robot operating systems. Uh, there are different challenges of using robot operating systems, but I'm not going to say what are the pros and cons of the robot operating system. What will be a better change or a better solution instead of using robot operating system. But this is something that at least Apollo is using, and other systems are also using that. So there are some terminologies that are used. Maybe I just have to say this quickly. Basically, everything like modules are interpreted as nodes, and we can say that simply a node can subscribe to a topic, which means that the node reacts to incoming message of that specific topic. For example, a node can be a perception module, and a topic can be, for example, camera data. So whenever the camera data arrives to the module, it can react to the system. The node also is able to publish on a specific topic, which basically sends messages about the specific topic. We have callback functions, which are actually functions that are reacting to messages of that topic to which it is linked. And also we have a spinner, which is a very well-known rows class, which executes all the callback functions that are triggered during the runtime until the system is terminated and it's shut down. So now I would like to go to the deep learning in autonomous driving. Before that, I'm I'm trying to see whether there is any question. Uh, so there is one question. Thank you, Hamid, for the presentation. We heard people talking about autonomous driving since more than 5 years or more. Why things didn't progress? How the HiPEAC community can help, and where? Uh, I I don't think that I'm agree with you that there is not much progress. In fact, it's the otherwise. We have seen huge progress in the academia and also industry, but I don't know if it is always like this, which I don't think so, in fact. But autonomous driving, at least, is a domain that I believe the industry is far ahead of the research communities uh, for for some reasons that at least it is not very clear to me. So we have a lot of advanced and improvements in the industry that is not still reflected to the research community. Usually, it's the other way around. Like, for example, I give you an example of the computer architecture community, which the researchers are always proposing some solutions which can be used in the architecture, like maybe even years later, and still it's a valid contribution. But in autonomous driving, if the industry is not behind, I mean, is not far ahead of the community, the research community, they are not behind the research community. So maybe this is one of the reasons. And the other is that, I mean, this is more looking like a product, or I would say in some aspects a challenging topic, because we have many things involved, from safety to things related to deep learning. But I think we had quite good improvements and advancement in the past few years. So I will discuss later what are the latest achievements in this domain by the research community. So let's focus on deep learning in autonomous driving. Basically, deep learning, like many other domains, have changed significantly the game in automotive industry, because before the use of deep learning and its successful outcome on many things like computer vision, which is very, very helpful for autonomous driving systems, we had traditional algorithms and traditional computing systems in cars, and car manufacturers were using them. But now we are seeing that deep learning is providing significant benefits for things like computer vision, which is widely used for modules like perception, which in fact you are able to process an image and saying that which objects are there and what is the probability of an object uh, with this detection, and a lot of other things for the path planning and trajectory prediction. All of them are widely using deep learning solutions. So I would like to share with you our observation on seeing how deep learning is, for instance, implemented in Apollo. We have seen that different forms of deep learning, like deep neural networks or recurrent neural networks, have different instances in Apollo with different workloads and durations and periods. In one of the basic configurations of Apollo, we have seen that we can have um, more than 5 or more than 7 deep learning instances that they are actually running concurrently. We have deep neural networks for speech recognition. We have other neural networks for object detection, for traffic light detection, for detecting objects from LiDAR point clouds, and all of them are using deep learning. For instance, in the perception module, we have camera-based object detection, which is using a convolutional neural network to identify objects and traffic signals from a camera sensor. We have, again, another neural network for detecting objects from LiDAR point clouds. We have we can have actually a deep learning algorithm to track objects if we are not willing to use traditional object tracking algorithms. For modules like prediction, we can have recurrent neural networks for lane sequence tracking, and also for tracking the obstacle status. So there is a lot of variants and instances of deep learning widely used in all autonomous driving systems today. And in fact, here I would like to show that, I mean, all of these instances can simply run in parallel, and they have to, in fact, run in parallel, because each of them are responsible for doing specific tasks. So I will later go in more detail about this, but having a projection of the deep learning instances, we can simply have more input sensors. What I showed you was in the earlier slide, it was just using one camera or one LiDAR sensor, but in reality, for achieving full autonomy, in fact, we need 360 degrees vision on the surrounding of the car, and that simply means we have different cameras on the autonomous vehicle. And not only we have different cameras, but we have different types of cameras. We have wide range cameras, we have long range cameras for detecting objects that are far from the car. And in fact, today we have autonomous cars like Tesla in mass production that they are using several sensors and even several heterogeneous sensors like radars, multiple radars, and multiple cameras. Another direction is that we are going to see, in fact, more sophisticated algorithms to increase the accuracy, because the more we want to have accuracy in our system, it is inevitable to use larger and more complex deep learning models with more number of layers, that deeper networks, and more number of weights, and increasing the dimension of the model. In fact, we have DNNs which are using more and more layers to improve the accuracy. We have now deep learning models which are using more than 100 layers only for camera object detection. And this is something that simply can be more sophisticated even in the near future. Apart from all these, we have another direction, which is simply adding more functionalities to the system. Now we have more sophisticated features like things related to the in-cabin features like gesture control, driver monitoring systems, which monitors the behavior of the driver, whether he's fully aware of the surrounding, the driver is awake, or other things, and all of them are using deep learning for this purpose. So as a simple conclusion for this projection, we see that all these directions, when we are moving towards this, each of these directions, it will be simply translated into more computation power and more deep learning instances. So now I would like to say what are the computing elements that we are going to use in autonomous driving systems. Basically, we have multi-core CPUs which are used, but this is unfortunate that the computation requirements by advanced autonomous driving systems are far beyond the capacity of any multi-core or many-core CPU. For this reason, we have the GPUs that the latest GPUs we have still the CUDA cores or regular cores. For example, I'm talking about NVIDIA GPUs, and we have in the latest architectures specific architectures for doing matrix multiplication and deep learning acceleration, like the tensor cores. And also we can have specialized accelerators or commercialized existing deep learning accelerators, like the one that NVIDIA is already shipped in the Xavier SoC system on chip, which is called NVIDIA Deep Learning Accelerator. So we have a variety of computing elements, each of them with different features and advantages and disadvantages, and all of them are usually used in modern autonomous driving systems. For instance, you see that now we have the feature to use tensor core, and it is simply required to modify some of the parts of the code, like setting a math mode, for example, in this specific example, and to have the data in multiples of 4 for the Xavier architecture, in the Volta architecture, in order to get benefits of the tensor core, which is much faster and more energy efficient than using the GPU traditional cores. Now, I would like to discuss about some performance constraints that we are having. Basically, We have frame rate, which is one of the important things. So the sensors are capturing data in a specific frequency. For instance, the camera is capturing at 30 frames per second or 25 frames per second. So this is one of the important factors in order to determine the performance requirements for the system. Also, the latency of the system is very, very important because uh, from the moment that something happens in the scene uh, until the moment that the autonomous vehicle is recognizing the change and going to make some decision and react, it should be fast enough that the system is able to control the situation. Here are some of the studies that have been lately basically uh, measured. Normal people are reacting to a possible interruption or something that is happening in less than 1 millisecond, in around half a millisecond. It takes almost 1 second to release the accelerator. Sometimes it takes up to 2 seconds to reach maximum braking. And also studies shows that it takes like 1.64 seconds to begin steering to avoid an accident. This is these times are much less for very professional and advanced drivers like the drivers of Formula One, which they are able to make these decisions much faster in around 100 or 150 milliseconds. So from what we observe from the human driver, the system for autonomous driving should be at least as equal as a very good driver. Otherwise, it is not going to be very safe and, and useful. So most of the data analysis shows that the latency for processing the traffic conditions should be within 100 or 200 milliseconds, not more than that. We have predictability constraints. This is another set of constraints. I will go through this in more detail later when I am talking about the safety critical systems and saying that all the autonomous driving systems fall into uh, safety critical domain. But basically, the performance of autonomous driving systems need to be extremely predictable in order to be adopted. And there are a lot of solutions or studies on that, but it simply suggests that the using measures like tail latency, which are defined as high quantiles of the latency distribution, the system should be very predictable. Basically, as a conclusion, we can say that due to large performance variability of the autonomous driving systems, we should use measures like tail latency. But I mean, this is a very simple measure, but at least something like tail latency in order to evaluate the performance and identify the predictability requirements. Another set of constraints are, in fact, thermal constraints. We have here two constraints. One is the temperature of the space to hold the computing system, which it needs to be within the operating range of the system because the system is simply using chips and computing elements, and they are silicon, so they are having a specific requirements in terms of uh, temperature in order to operate in their best conditions. And also the heat that is generated by the system itself should be relatively small in order to have a small impact on the thermal profile of the vehicle. So I am going to discuss where the system should be actually located in the vehicle, which in every vehicle we have usually two temperature zones. One is the engine zone, which usually is very hot, and the temperature can simply go above 100 degrees, and then this is absolutely not suitable for computing elements. Uh, then the other space that is remaining is the passenger cabin, or the climate controlled part of the vehicle, which it is controlled, the temperature is controlled. So we need additional cooling capacity in order to improve the cooling of the cabin if we are going to generate a lot of heat because of these computing elements that we are going to put in the cabin. We have also power constraints, because the system is going to use a lot of power, and that simply will affect the driving range of the vehicle. If we want to have a computing system in a vehicle, it needs the power for running the system and also some power for cooling it down. So some analysis shows simply that if we are using sophisticated systems like three GPUs, or for example, GPUs and CPUs, you see that even the driving range can be reduced by more than 10%, which is quite significant, because we have hundreds of watts only spent on the power of the system itself, and also we need a lot of energy to reduce the heating and also cooling down the system. So that simply translated into reducing the driving range. So now I'm going to discuss about the timing characterization on different computing elements. I have already discussed what are the computing elements that are used in the GPU for the autonomous driving system, such as GPUs, different computing units. In fact, in GPUs, we can have specialized accelerators. We can have still CPUs or multi-core CPUs for running main tasks or controlling the other computing elements. So let's move on to this section. Basically, here I would like to show uh, 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 an architecture which is for NVIDIA Xavier system on chip, which is composed of octa-core CPU with 4 clusters of dual-core Carmel processors. We have a quite good GPU, which is considered as a mobile GPU, with 8 streaming multiprocessors and 512 cores. It also implements the Volta architecture, so that it has tensor cores. And also inside the same chip, we have 2 instances of the NVIDIA Deep Learning Accelerator. So we have quite heterogeneous architecture and computing elements in a single system on chip. And in fact, this is especially designed for autonomous driving systems, and it is integrating more than 7 billion transistors. So I would like to show you these results that we have observed, just to see how powerful are each of these computing elements. Here we have different instances of or functions of an autonomous driving system in Apollo. For example, here we have 2 object detection units, one which is using a smaller deep learning model, and the other has a larger and more sophisticated model. You see that usually when we are increasing the number of cores in the CPU, we get a good speed up, although it is not exactly linear. We know the reasons, but I mean, it is quite still significant. With using the GPUs for the same task, we are able to, in fact, get like 2 orders of magnitude speed up for the same task. And using the deep learning accelerator, in fact, we are getting further speed ups in comparison with the GPU. So at least for these two benchmarks or two functions, the deep learning accelerator works great. This is the same. We have another object detector with a different model, deep learning model for processing the point clouds of LiDAR and also for the object tracker. And you see that the trend is more or less the same. It's worth mentioning that in some cases, like here, what we are seeing is that we always expect to have the tensor cores providing more performance and in fact faster results, but it is not the case always, because using the tensor cores has some overheads, and if the workload is smaller than a specific size, it is not worth tolerating that overhead. And you see that, for instance, for this specific task, the tensor cores are providing slower performance than using the GPU itself. This is the same for the NVDLA, because it also has some launching overheads. For instance, here you see that since the neural network that is used for speech recognition is quite small, the overhead of launching the deep learning accelerator is not worth to launch the application in these instances of NVDLA. And in fact, the GPU provides better performance. So now, with having a background and introduction to the autonomous driving systems, what they are, what are the performance requirements, why we are using GPUs, in fact, due to the huge performance requirements by these systems, and all the things that I already discussed, I would like to continue our discussion by moving forward and talk about safety standards and certification requirements for autonomous driving systems, of course. So what is a safety critical system? A system is considered as safety critical if a failure or malfunction result in death or serious injury to people, loss or severe damage to equipment or property, and also it causes environmental harm. All of these, if can happen in a system, that system is simply considered as a safety critical system. And we have various examples of that. The most well-known are airplanes, automotive vehicles, railway, radioactive domain. And each of these domains have specific safety standards which are responsible for providing guidelines and requirements for each of these domains. So the standard that is covering the requirements for avionics is different than the automotive domain. So the thing that is common in all the safety critical systems is that they require exhaustive verification and validation process to guarantee the safety goals are met. And this is very, very important in all safety critical systems. And as I said, each domain has its own guidelines and regulation for both hardware and software. So let's see what is validation process. We have timing validation, which is focusing on showing that the timing budgets which are derived are not violated. The application should be behaving in the specific time that is given to the application, and that should be met always on time. The absence of violations serves as evidence for certification purposes on the timing correctness of the system. And in fact, validation techniques rely on the ability to collect information on the execution of the tasks under analysis. So we have different approaches. We have software resource usage testing, which is an attempt to ensure that the unit under test does not consume an excessive amount of execution time or memory. So the system has to go through excessive amount of tests in order to fulfill all the requirements by the safety standard. Now let's focus on the ISO 26262 safety standard, which is the main functional safety standard for road vehicles. It is providing guidance on how to develop automotive safety related electric and electronic systems. So anything in a vehicle that is using electric and electronic, it has to go through the certification of this standard. It can be an ABS system, an airbag system, whatever electric system that is inside the car has to go through a certification process. The standard also identifies the safety goals and requirements for different software items in a vehicle. It also propagates safety requirements to each specific item. So we have a terminology which is called Automotive Safety Integrity Level, or ASIL. Basically, ASIL is that each item that has an attached ASIL, it can range from ASIL A to ASIL D. We have ASIL A, ASIL B, ASIL C, and ASIL D, which D is the most stringent safety integrity level. And all items with some ASIL, they have to go through a verification and validation process. We may have some modules with no safety requirements, which are tagged as quality managed. So here we have a famous model, which is called the V model of the ISO 26262 safety standard. Here in the left side, we see basically the design phase, which we have the system design, the specification of safety requirements, the software architectural design, software unit design and implementation. And in the right, we are, after the design phases, we are going through test phases, which are software unit design and implementation, software integration testing, verification of software safety requirements, item integration and testing. And this can be done in, I mean, this is very simply shown here, but there is lots of details for each of these steps to be performed. So here, after, for example, a specification of the technical safety requirements, we are moving towards the safety design. And in fact, we have two parts, one which is product development at hardware level, and the other is product development at software level. And after that, we are going to perform the hardware software integration and testing. We have, as I said, the resource usage testing, which the aim of resource usage testing is to process during hardware software integration phases. And we are measuring minimum and maximum execution time, measuring memory requirements for code, data, stack, and heap. We assess whether the task scheduling allows preserving all the safety timing constraints and a lot of other things. So in fact, the standard provides guidance on software production. It lists for each of the process what are the safety requirements. Here we have the activities which we need to do to fulfill those requirements which are specified, and then we need to show evidence that all these requirements are met, and then this process can go lots of times in order to fulfill all the requirements. We do the traceability, in fact, which is, as I said, is fundamental to link high-level requirements and low-level requirements and analysis. So now I would like to emphasize what are the existing problems that we want to discuss about. In fact, in autonomous driving software, uh, we have done lots of extensive analysis on Apollo and several other uh, existing and open source autonomous driving systems. But here I'm just talking about Apollo. We have seen that the system simply is not designed according to the ISO 26262 guidelines. We have observed lots of misalignments between the standard and also the software, which is Apollo in this case. We want to see how to certify this autonomous driving software according to the requirements of the safety standard. So it is not something that is recommended or it is just some form of guidelines, but the system in fact has to implement what the standard says and passes all the requirements of the standard. So this is very strict requirements, and otherwise the system cannot be certified and uh, going through mass production. So I will discuss, and you will see that we are identifying some issues which are hampering the autonomous driving heterogeneous software adherence to ISO 26262. We see that how GPU code can be aligned with the requirements of the safety standard. And also, we would like to provide some key insights and research directions to address some of these existing challenges that we are observing in autonomous driving software. So let's focus on the safety life cycle. We have hazard analysis and risk assessment, which is basically identifying hazards and also assess the severity, exposure, and controllability to determine the AC level. And after we are determining what AC level we are, we determine the safety goals. So we derive functional safety requirements from our safety goals. We allocate these requirements to architectural elements, and this is going to be successively refined. I mean, as technical requirements at system level, and also later as hardware and software requirements. So we'll discuss this in more detail. So we said that we are going to refine the here we say that we are going to successively refine uh, these requirements. And then once we are refining the requirements to the software level, the development process should follow according to the V model. We have things related to a specification of the safety requirements, architectural design of the software, unit design, implementation, unit testing, integration testing, and safety requirement verification. So in this session, I'm going to discuss a bit about architectural design, unit design, implementation, and unit testing, but there are a lot of other things related to other topics like safety requirement verification, integration testing, which we cannot cover in this session. So let's start with the software architectural design. So when we say the software architectural design, in fact, the standard, the ISO 26262 standard specifies coding and modeling guidelines for the development phase at software level. It has specified different features to be provided by the software for different AC levels. So here, to understand this table, we have three different forms of requirements. We have plus plus, which is highly recommended or it's mandatory. We have 1 plus, which is recommended, and we have O, which is not required. As you see, for instance, all the items in this table are highly recommended or mandatory for the ASIL-D level. For the ASIL-A, for instance, some of them are strictly required, some of them are not required, and some of them are recommended. For instance, we have enforcement of low complexity, which has to be totally fulfilled for all the ASIL levels. Also, the use of language subset has to be uh, totally fulfilled for all the AZ levels. Using, for example, defensive implementation techniques can be avoided for ASIL A units, but for ASIL C and ASIL D still is required, and so on and so forth. I will go through some of the in the following slides. Let's talk about, for instance, the enforcement of low complexity. What we did with Apollo, we just extract the cyclomatic complexity, which is a measure for deriving the complexity of the software, the number of lines of code, and also the number of functions in each of the Apollo modules. So the cyclomatic complexity is a value, uh, like it can be uh, 5, 10, 50, anything like that. So when this value is between 10 to 20, it is called moderate. Of course, below that, it is not complex at all. From 20 to 50, it is called risky because the software is quite complex. And more than that, the software is almost unstable because it is so complex that we cannot have a clear understanding of its behavior and all the possible scenarios that can happen to that piece of software. So you see that for different modules of Apollo, like perception, localization, planning, and so on and so forth, we have tens of functions which are moderate. We have, again, like 20 functions which are risky in terms of cyclomatic complexity, and also some of them which are totally unacceptable because they are more than the 50 threshold. And in terms of complexity, like lines of code, we see that each of these modules have tens of or hundreds of, uh, sorry, thousands of lines of code, and also hundreds of functions. So the software is quite huge. The whole Apollo is uh, including like hundreds of thousands of lines of code, and that is not a simple software, although it is written somehow efficient, but it is quite big, and the software is complex. What we have observed is that, as I said, there are several modules with high cyclomatic complexity. It is very important to reduce the complexity in order to maintain the verification costs. And also, we facilitate the timing estimation in terms of worst case execution time. Another item which was mentioned was the use of language subsets. So the objective here is that we facilitate the code assessment in critical systems. So for instance, for the CPU, we have different language subsets defined. One of them, for example, is MISRA C, which is well known in automotive. The CPU part of the Apollo, we have seen that it is not programmed according to any safety-related guidelines. The good thing is that it is possible to change the code in order to adhere to one of these language subsets like MISRA C, but this is for CPU. For GPU, in fact, we have no guideline in the standard or language subset existing for GPU code in order to facilitate code assessment in critical systems. I don't know if you may be aware of that or not, but usually the safety critical domain are using architectures which are far behind the state-of-the-art architecture. For instance, it may be surprising, but still in avionics, they are using computing elements that are belonging to decades ago, or even they are not using still in some cases multi-core processors. So using a GPU is totally something it's considered as a radical change for safety critical domain. That's why still we don't have any guideline or language subset for GPU. The CUDA, which is belong to NVIDIA, the CUDA code intrinsically uses features which are not recommended for CPU in ISO 26262. For instance, the standard highly uh, recommend not to use dynamic allocation, dynamic memory allocation or pointers, but all of us know that this is one of the basics of CUDA to have dynamically created arrays and pointers. So in fact, continuing with the software unit testing for the CPU code coverage, we have an objective, which is to check whether our tests provide enough coverage or not. The standard requires always to have a very high code coverage, which is 100%. And also the code coverage for the autonomous driving software, we have observed that it is quite low. Here we see that for one of the functions of object detection, we plotted the statement coverage, the branch coverage, and modified condition decision coverage, MCDC. And you see that according to the standard, which requires 100% coverage, we are far from being 100% in most of the functions. And it is interesting that here in this plot, we only plotted the functions that are called in the application. In fact, we had lots of code and functions which are not called. And if we want to include that, the coverage simply could be 0. And that is very bad for the software according to the standard. And that is not acceptable. So we need additional test cases in order to achieve high coverage for this. And also there are a lot of requirements in order to improve the coverage, like branch coverage or MCDC coverage. Regarding the GPU code coverage, we have the problem is even worse because we have limited tools in order to which are able to support in the real-time domain to measure the GPU code coverage. For instance, at the time that we have been doing this analysis and this research, we didn't have any code coverage tool which is qualified to analyze GPU code coverage. So the software unit testing, we have the safety standard, which requires us to assess the code coverage. And also another important thing is that the code coverage, when we want to do it, apart from whether we have the suitable tool or not, the code should be available. This is another problem that we are facing in automotive, and at least what we have observed in autonomous driving systems. What that means is that in these systems, we have seen extensive use of highly optimized closed source libraries like NVIDIA CUDA libraries, which are highly optimized for performance. And in fact, we don't have the source code. It's just the library which is there, and we don't have any available source code to perform any form of code coverage. The code coverage is only doable when you have access to the source code. And in fact, we cannot do that because simply the code is not there. And this hampers assessing compliance against ISO 26262. We have many libraries that are used in Apollo and several other autonomous driving systems, including the ones of NVIDIA, like QDNN, QBLAS, TensorRT, and many others, which are not public, and the library is closed source, and we cannot do anything to make code coverage. There are some suggestions like, what if the vendor is going to perform these tests? But this is something that is, it is not so easy to do so because of many reasons that is out of the scope of this talk. But I would like to here just emphasize that what are the simple challenges that we are seeing, and they are basically putting a big question mark under these requirements of the safety standard. So what if We have open source libraries. Do they solve the issue? We said that using closed source libraries are a problem, but do we have any solution or equivalent open source libraries which they can solve this issue? Do they provide competitive performance in comparison to the closed source libraries? Well, we did some analysis, we did some experiments. For instance, as a competitive or as a replacement for some of the NVIDIA libraries like cuBLAS, we used NVIDIA's open source BLAS library, which is called cuTLAS here. And in fact, we did some experiment, and what we got, it was in some cases like here, even providing very good and close performance in comparison with the closed source library. There are also other libraries available for these uh, deep learning libraries like cuDNN, which is called, for instance, HiPEAC. We have also the results of comparing HiPEAC with cuDNN of NVIDIA, and you see that in some cases we are close, and there are some cases that the performance is even up to 40% slower. I would say this is a good beginning for this, but you may know that these libraries are always under development and improvement, and it is very difficult to keep this competence close because there are many developers in the industry and in these vendors are just improving their software, and this is not the case for open source libraries. So this gap may be increased very quickly, and maybe now it is already much slower in comparison with the latest releases of the, uh, the recent libraries of NVIDIA. And the other thing that is important is that in the libraries that are usually closed source, we have a huge amount of functions and uh, um, features which are simply not covered, all of them in the open source libraries. This is the case even for cuTLAS, which is although developed by NVIDIA, but it is not featuring all the capabilities of the cuBLAS. So these are the two main problems that we are seeing with open source libraries. But at least if there is no way to do the code coverage, neither by the vendor or we don't have the source code, the use of open source libraries can be a solution at least. We have other things related to software unit testing, which the standard simply specifies requirements for architectural design of the software. You see that there are a lot of things specified in detail, like appropriate scheduling properties, restricted use of interrupts, and even for software unit design and implementation, like initialization of variables, no multiple use of variable names, avoid global variables or justify usage, a lot of things, limited use of pointers, no explicit type conversion, and a lot of other things that have been specified by the standard. So in fact, the ISO 26262 provides several guidelines to ensure features such as simplicity, correct order of execution, consistency of interfaces, and data control flow. So we observed that at least Apollo and some of the other existing open source autonomous driving software are not completely comply with the principles for unit design and implementation. We have seen that part of the code can be modified with some effort, and we have some more challenges which are not as simple as modifying the code, like the libraries and a lot of other things that I couldn't discuss in this session. But this analysis simply shows that either we have to move towards the requirements of the safety standard, or the safety standard has to propose some alternative solutions for the industry and the community of automotive. So just as a summary for this part, I provide you an assessment of safety properties of an industrial GPU accelerated autonomous driving framework. We have identified complexities and missing features in order to adhere to ISO 26262 safety standard principles for software. We didn't talk anything about hardware, but there are also a lot of requirements for the hardware as well. We proposed different approaches to handle some of the complexities, like using the open source libraries or simply modifying the code in order to adhere to the requirements of the ISO 26262 software guideline. And also we have highlighted several challenges towards certifying GPU code according to the requirements of ISO 26262 standard. So now I would like to continue with roadblocks on resource usage testing on autonomous driving software. Basically, we don't have any new questions, so I can continue. So resource usage testing is also one of the key requirements of the safety standard and has to be performed. One of the things that I would like to start with is the resource usage testing in GPUs. We have lots of tools like the ones that are provided by NVIDIA if we are using NVIDIA GPUs, which is most likely the case, especially that now NVIDIA is the dominant provider of platforms for automotive domain. We have NVIDIA Profiler, NVIDIA Visual Profiler. So we have seen that we simply can face lots of issues, such as blocking the execution process because the execution of the module seemed not to be progress at all, because the system of Apollo, for instance, was not simply working as we are profiling other form of software. So we did some hypotheses like slowing down the execution. We stopped the execution time. We did some experiments and ran the experiments for lots of hours to see whether we see any progress. We use debug messages, for instance, in different parts of the modules, and none of them have been, in fact, run. And well, that was seeing, in fact, no execution process at all. The execution of the module seemed to be not progressing, and even with the modules that are not using GPUs, that they are supposed to be running in the GPU, we have seen a lot of issues. So what we did, we had another hypothesis that the CUDA calls, which are going through threads and also the robot operating system nodes. We use some synthetic applications to write some programs to create multiple threads that they are launching CUDA kernels, and we went through the ROSE node and all the things related to this to the C++, and in both cases we were able to do the profiling, but it was not working with the Apollo. Then we suspected that there are some issues with the libraries, and finally we were able to solve the issue. The other thing is that the CUDA kernel identification, basically we have tried to identify what are the required versions of, for instance, Caffe, which is a deep learning framework, to work with the Apollo. And also the CUDA calls are performed through a number of function calls that increase the difficulties to trace what particular calls are used and where in the code. We had another issue, which was lack of support for memory usage testing, because as I talked earlier, the resource usage testing, it also is about the memory usage, and it needs to determine the resource requirements at fine granularities to help the optimization and debugging during the development process. We see no suitable tool for allowing the collection of this information for GPU code in a very straightforward way. So all of these have been happened. So regarding the CPU resource usage testing, it was more straightforward because we have powerful tools like the Google Performance Tool. We have other profilers like Valgrind or Perf. And we see that Apollo developers have used the Google Performance tools integrated in order to provide the profiling of the framework. And we have some results that turns out to be disappointing, because that was not what we expected to see, because even although the system was supposed to profile, in fact, it wasn't doing that. So we used another profiler that is Perf here, as I said. It provides at least better results, but failed at some of the modules like perception. So we couldn't do any profiling. All I'm saying here is that even simple things like profiling or resource usage, like memory consumption, is not so trivial with complex systems like autonomous driving software. And that has several reasons, because first of all, they are using multiple libraries and complex integration of software, which are from different vendors. The other thing that is very important to mention, and I didn't say that before, is that usually these frameworks, due to the complexity of installation and compilation, they are shipped in a series of Docker images. And then when you want to communicate from the host to the Docker, there are some other issues that can happen, which just make things more complicated. So we proposed a series of guidelines, which we called it en route. In fact, this is a paper which we published this year in Symposium of Applied Computing, which we just proposed several sets of guidelines to enable resource usage testing for autonomous driving frameworks based on our observation and our experiments. We basically, for the GPU guidelines that that address previous the issues like the execution process, CUDA kernel identification, and the memory usage testing, also some CPU guidelines. So regarding the execution process, basically we see that we can simply disable profiling from the start of the execution by using a command, and stop execution to collect profiling information at a specific time using a timeout. This is necessary because Apollo is intended to run continuously, because the system of autonomous driving is intended to run continuously until the user shuts it down. And also, we see normal execution can be stopped with a signal of sigint, which is a simply Control-C in Linux terminal. And when we are profiling, the signal is received by the profiler, and the profiling information is not collected. That's simple. So we did some tricks just to put the profiler here to identify the region of interest that we want to profile, starting from a specific point of the code and stopping at a specific point of the code. And regarding the second issue, basically we inspect the functions of all nodes of, for instance, perception, to identify the CAFE framework and Apollo's functions that we need to be profiled, and we profile all the function to relieve the end user. from having to track what functions are used in practice. And we did this through a Python script that automates this insertion of profiling calls. Regarding the memory usage testing, we use a combination of tools like the GNU Project Debugger or the GDB, and also the NVIDIA System Management Interface, the NVIDIA SMI. We need a user intervention to determine basically the granularity at which the memory usage must be assessed. We introduced some breakpoints during the execution of the application at corresponding locations, as you see here, and we query the actual memory usage by using the NVIDIA SMI. Regarding the execution time for CPUs, we have found no tools that provide appropriate support for autonomous driving frameworks. Well, this is, we believe that an engineering work is necessary to build the call tree of complex modules like perception, because none of the tools that are there are able to perform that. And also, using this information, we should be able to use timers to be placed in precise locations to collect execution times at the desired granularity. So regarding the memory usage for CPU, we used again Valgrind with the massive tool of Valgrind. And what we see here, just I would like to show the execution time breakdown of Apollo perception here. Basically, you see that for two configurations, which one uses LiDAR as main object detection unit, and also the other is based on camera. We have this execution time breakdown, which mostly is performed in the LiDAR. To process the radar is not that compute intensive. The fusion is somehow compute intensive, but this is mainly because the fusion is done in CPUs, and the LiDAR is accelerated to execute in GPUs. This is the same with the camera and also the traffic light process. So here we see again the timeline for camera and LiDAR configuration. You see that in which frequency these functions are executing. The radar has to be processed in a higher frequency, because every 10 milliseconds, the radar produces some information that has to be captured and has to be processed. But the frequency of producing the data for camera is around 25 or 30 frames per second. For LiDAR is around 10 frames per second. So regarding the execution time usage testing, we just observed that the dominant functions are the matrix multiplication, which are the gem functions in the GPU, which are consuming most of the time, and also the image to call function, which converts the image into the series of matrices to be performed by the deep learning. And this is another function which is also provided in deep learning frameworks like Caffe. For memory usage testing, we see that the memory usage for camera and LiDAR configurations, we see that they are requiring gigabytes of data. So here we see that for a simple configuration that is using I think this one is LiDAR, yes, this one is camera. Here we are occupying around 1.5 gigabyte of memory, which the dominant part is related to the deep learning processes like traffic light preprocessor and also the traffic light process. The robotic operating system also occupies hundreds of megabytes of memory. And this can simply increase a lot by having more sophisticated configuration. So now I would like to move forward with basically the timing analysis of autonomous driving software as our last section. Let me see whether we have any questions. Uh, well, we have one question. Have you considered using TAU for performance measurement? Um, well, I think we didn't do that, but we can consider this and do some experiment with it. And for sure, if there is something interesting, we can share the result with you. Thanks for the question. So one of the other important things, well, we have one more question. Uh, Thanks for the question. What is your opinion about the usage of programmable logic, FPGA, instead of GPU in autonomous driving development? Actually, I didn't mention the GPUs, but in fact, sorry, the FPGAs, but in fact, FPGA is also a very valid option for accelerating some of the units of uh, deep learning, and also maybe for other modules of autonomous driving software stack. Uh, One of the things that we all know is the challenge and the trade-offs between the complexity of modifications and implementation on FPGAs in comparison with GPUs. Uh, I believe that uh, still we are in the early phases of development and research for autonomous driving systems, that the algorithms are tend to change a lot, and also they are quite unstable in terms of providing enough accuracy that is required. Uh, Most of the, the algorithms, the modules, we see that they are highly under modification and optimization. And probably once we have a more stable version of code and something that is quite stable, then it's worth to exploit the benefit of using FPGAs, because for sure they can be a lot of they can provide a lot of benefits, especially in terms of power for the systems, at least in comparison with the GPUs. We know that the ASICs are probably the most difficult to design and also to modify if the ASIC is not going to be changed. But they are providing the highest performance and energy benefits. So still we don't see that much also uh, stable releases of ASICs. We recently heard about Tesla that they are shipped their own system on chip, which is a specifically designed accelerator and system for themselves. We are not aware of the architecture because it is closed. The information is not public, but I believe that in some aspects they have reached some stable situation that they are able to focus on designing an ASIC rather than using GPUs anymore. So, but for sure, FPGAs are very helpful. Nowadays we have very powerful GPUs and also FPGAs. So both of them can be used extensively in this autonomous driving domain. So let's continue with the last section. I said a lot of things related to constraints in terms of performance, in terms of predictability, in terms of safety standards. And one of the other important issues that we are facing is the timing variability that we are observing in autonomous driving systems. So here you see that I am providing whisker plots of execution time for different modules of Apollo, from perception to map. You see like all of them almost. And you see that the variability can be quite significant although the function may be using the same thing, but this is depending on many factors, not only the function itself. So I'm going to discuss a bit about what is the reasons that is happening and why we are observing this much of variability. So basically, I am going to just provide you some of our contributions that we have published in this RTAS conference. Basically, we provide an in-depth analysis of timing variability for autonomous driving modules. We did some measurement-based timing characterization, also an analysis of sources of variability, which is very important, and also the challenges that randomization, large input data set, and execution scenarios create to apply established timing analysis approaches, and also some statistical support. So for Apollo execution time, basically we have did that at module level to perform the analysis. And here you see that basically what we are observing, we perform some analysis to measure the minimum, the quartiles, the maximum, the CV, the variance, and a lot of other metrics that I just summarized some of them here. You see that, for instance, for the perception module, the ratio between in fact, the maximum and minimum is 11.9x, and that is huge for a function like this, and also for prediction that can be even more, like 21x, which is a huge amount of variability. So we wanted to study what are the sources of execution time variability, because this is quite important for us and we need to understand why this is happening, in fact. So what we did was to see whether this source of variability is platform or not, or how the randomization and non-determinism of the algorithm is affecting. For instance, we have algorithms that simply can be randomized, and they are non-determinism, and every time based on a given behavior of the application, the timing of the application can be simply different, like the ransack fitting algorithm. We also studied the impact of input data to see how much is the impact of input data on the execution time variability. And also we for instance, as a case study, we observed the execution time variability on the ransack algorithm. So let's show you some interesting results. What we have observed here is that in terms of platform, when we move all the other equations out of the problem and we just focus on the platform itself, we see that the platform is causing something like 15 to 20% or even less than that in terms of time variability. So having this impact of 15 to 20% cannot be the result of something like 20x or 12x that we have observed in the modules like perception. The other thing that we have observed is that what will be the impact of input data and parameters. So we have used different forms of input data, for instance, and we observed that yes, this is this even can be very significant, because here you see that the impact of the input data can be quite significant. And in fact, this is something very important for us, because the impact on the accuracy, the impact on the execution time here is in order of 2 orders of magnitude. The same for the randomization and also the random values that can be happening in an application. we are observing that this is also in terms of two orders of magnitude, like 80x or 90x variation, and that is quite significant. So one conclusion that we can make is that for sure the platform is not providing that much, and it's not contributing that much in the execution time variability, although it is important. But we have concluded that the input data and also the random values in some of the applications can simply have a huge impact on the execution time variability. So I think we are quite on time. I didn't focus more on the timing because there are a lot of things related to the further analysis that we have performed in order to understand and analyze what are the reasons that this variability is happening and how we can uh, provide some form of assurance that this can be controlled, or with some probability we can have an worst case execution time estimation for these systems. But I'm afraid that that will be a little out of the scope of this talk, because I wanted to keep the discussion generic and useful for the attendees. I would like to provide you some of the references that we have used. Basically, these are some of the works that we have recently published in real-time conferences, and also in symposium on applied computing, again in the ECRTS conference last year, in the DAC conference, in IEEE Micro magazine. Some of these discussions that we had today are described in more detail in these references. I would like to acknowledge the projects that we have, the ERC Supercom, which is sustainable performance for high performance embedded computing systems, and also the recent project that we have, FTI Mastex, which they are partially funding this work that we have been doing in PSC. And I would like to thank you for your attention, and I am staying available for any question or any suggestion that you may have, and we can discuss. Of course, you have my email in this slide for further information and discussions. Should you require any further information, or you are interested in any of this material that I am discussing, feel free to contact me, and we can discuss further offline. I see one answer for the latest question regarding the FPGA. Basically, there is an answer which is saying that, particularly taking the benefits of low latency in FPGAs, which is important in autonomous driving domain to respond the input sensor signal. I mean, this is quite important. As I said, the FPGAs have lots of benefits for us. There's no doubt of that. But what we are suspecting is that I think that we are still a little. It is still too early for the industry to focus on implementing and investing on FPGAs, because the front end and the software still is not that mature enough, so that we can just rely on improving the performance and the energy efficiency of the system. But for sure, with the powerful and very capable FPGAs that we have nowadays, for sure they are one of the true choices for automotive. Uh, I don't see any further questions. I will stay 2 or 3 more minutes in case any of you have any questions. Uh, okay, thank you for excellent. Thank you very much for your attention and your time. I think there is no much questions. I thank you all for attending this session, and also I thank you very much for the organizers of HiPEAC and the HiPEAC community that keep us together, and they do a lot of great work. Thank you very much. Have a good afternoon, and bye.